You look around, you see objects, solid things, a table, a chair. They're there, they have positions, they exist, whether you look at them or not. And that's what we all believe, that's common sense. When you go small, really small, down to atoms, down to electrons, reality stops behaving like reality. Imagine you're throwing tennis balls at a wall. This wall has two doorways, two openings, and behind the wall there's a back wall that records where each ball hits. You throw a ball, it goes through the left doorway or the right doorway, hits the back wall, leaves a mark. You throw another, same thing. After 1,000 throws, you look at the pattern. What do you see? Two clusters of marks, one behind each doorway. Makes sense, right? Each ball went through one door or the other. Simple. Now forget tennis balls. Let's do this experiment with electrons, tiny, tiny particles, the smallest bits of matter we deal with in everyday physics. We shoot electrons at a barrier with two slits, very thin slits, and we have a detector behind that clicks every time an electron arrives. Each click is the same, never half a click. So electrons arrive as whole things, individual lumps, particles. Good. Electrons are particles, just like tennis balls. But now we count where they land. We build up a picture of the pattern, and it's not two clusters. It's stripes, a zebra pattern. Lots of electrons here, almost none there. Lots here, none there. Alternating bands. Now this is what waves do. You see, when two waves meet, sometimes they reinforce each other. Bigger wave. Sometimes they cancel each other. Nothing. It's called interference. Like when two ripples in a pond cross each other and create a complex pattern. So, electrons are waves, but they arrive as clicks, individual lumps. We never detect a piece of an electron, it's always whole. Here's the situation. Electrons arrive like particles, but they arrange themselves like waves. Okay, maybe they're bumping into each other somehow, interfering with each other on the way. So let's slow everything down. We send one electron at a time, shoot one, wait for it to arrive, then shoot the next. They never meet. We do this very patient, one by one. Same pattern, stripes, interference. Each electron is interfering with itself. Now what does that even mean? Well, maybe the electron splits in half, goes through both slits, and meets itself on the other side. Let's check. We put a little detector at the slits to see which way each electron goes, and we watch. Every single electron goes through one slit or the other, never both. We catch it in the act. Left slit or right slit. It's a definite particle taking a definite path. But now we look at the pattern on the back wall. The stripes are gone. Just two clusters like tennis balls. Exactly what you'd expect from particles that go through one doorway or the other. So, when we don't look at which slit the electron goes through, we get interference. When we do look, the interference disappears. Let me say that again because it sounds insane. The act of observation changes reality. Now you might think, well, our detector probably bumped the electron, disturbed it somehow. Physics involves interactions, right? So let's be gentler. Let's use the softest possible way to detect the electron. We try this, and here's what Heisenberg discovered. There is no gentle enough way. If your detection method can actually tell you which slip the electron went through, it will always disturb things enough to destroy the interference. And if your method is too gentle to disturb anything, it's also too gentle to give you the information. You cannot have both. You cannot know the path and keep the pattern. Nature doesn't allow it. This isn't about our technology being bad. It's not that we need better instruments. This is fundamental, built into the fabric of reality. The electron doesn't have a definite path until you look. And when you look, you force it to choose. But wait, that's strange. Before we looked, where was the electron? Did it go through both slits? Did it go through neither? Did it take every possible path at once? We don't know. And more importantly, the question might not even make sense. See, we grew up in a world of tennis balls and doorways. Things have positions. They take paths. They're somewhere. That's intuition. That's common sense. But common sense comes from everyday experience. And everyday experience is made of big things. Billions and billions of atoms stuck together. At that scale, quantum weirdness averages out. You don't see it. But down at the level of single electrons, single photons, the rules are different. Our intuition doesn't apply. The words we use, like path and position and where is it, those words might not even mean anything down there. So when someone asks, but which slit did the electron really go through, the only honest answer is, if you don't measure it, the question has no answer. Not, we don't know the answer. The question itself doesn't apply. That's quantum mechanics. That's what reality actually is at the smallest scales. And if you don't like it, well, reality doesn't care what you like. Now let me tell you how we actually calculate things in this strange world. Because physics isn't just about being confused. We have to get numbers that match experiments. And somehow we do. Here's the trick. We gave up on predicting exactly what will happen. Instead, we predict probabilities, the chances. And to calculate those chances, we use something that sounds ridiculous. Arrows. Little arrows. That's it. That's quantum mechanics. Every way an event can happen, we draw an arrow for it. The arrow has a length, and it points in some direction. And here's the rule. To get the probability of something happening, you take the final arrow and square its length. But here's where it gets interesting. When something can happen in more than one way, like an electron going through the left slit or the right slit, we don't add the probabilities. We add the arrows first. And arrows are sneaky things. If you have two arrows pointing the same direction, you put them head to tail and get a longer arrow, big probability. But if they point in opposite directions, they cancel out, small probability, maybe zero. That's interference. That's why we see stripes. The arrows for went through left slit and went through right slit sometimes point together, sometimes point opposite, depending on where on the screen you're looking. But when you detect which slit the electron went through, you're not adding arrows anymore. Now you know it went through one specific slit, so you calculate the probability for that slit alone. No arrows pointing opposite, no cancellation, no interference. The math is simple. What's hard is accepting what the math means. We call these arrows probability amplitudes. And here's the strange part. They involve imaginary numbers, square root of -1, numbers that don't exist on any ruler. Yet when we square them to get probabilities, we always get regular positive numbers, real things we can measure. So reality is built on something we cannot directly see, using numbers that cannot directly exist to predict outcomes that are merely probable. Welcome to quantum mechanics. Now you might wonder, why does nature work this way? What's the deeper explanation? There isn't one. Nobody knows why nature uses probability amplitudes. Nobody knows why the arrows work. We know that they do. Every experiment confirms it. But the mechanism behind it, the reason, no idea. And honestly, that's okay. Science doesn't always answer why. Sometimes it just answers how. And if you keep pushing why this, why that, eventually you reach bedrock, the place where the only honest answer is, that's just how nature is. Now let me show you something even more peculiar. We've seen this business with electrons and two slits, but the same rules show up everywhere. You take a beam of neutrons and shoot them at a crystal. Now a crystal is just a regular array of atoms, all lined up in a nice pattern, like oranges in a crate. The neutron comes in, bounces off one of the nuclei, and goes flying off to a detector at some angle. Which nucleus did it scatter from? Well, there are lots of nuclei in the crystal, thousands. The neutron could have scattered from any of them. And here's the thing. These are indistinguishable alternatives. The neutron scatters, arrives at the detector, but there's no record left of which atom did the scattering. So we have to add amplitudes. And when you add them all up, you get interference. Sharp peaks at certain angles, almost nothing in between. Beautiful pattern, just like we saw with the two slits. Except now we've got thousands of slits interfering. But for some crystals, you also get a smooth background of scattering in all directions. What's going on? Well, we forgot something. The neutron has spin, and so do the nuclei in the crystal. Sometimes when the neutron scatters, its spin flips. And when that happens, one of the nuclei must have flipped its spin too. Conservation of angular momentum. Now, which nucleus flipped? We could tell in principle that nucleus is the only one with spin up. All the others still have spin down. The alternatives become distinguishable. So we don't add amplitudes, we add probabilities. No interference, just a smooth background. You see what's happening? For the no-flip scattering, we can't tell which nucleus was involved, so we get interference. For the spin-flip scattering, we could tell which nucleus was involved. No interference. The rule is always the same when alternatives are indistinguishable. You put the arrows together. When alternatives are distinguishable, you just count the chances separately. And you have to be careful about what distinguishable means. It's not about whether you bother to distinguish them. It's about whether you could, even in principle. If you could, even if you don't, they're distinguishable, you count the chances separately. If you couldn't, even if you wanted to, they're indistinguishable, you put the arrows together. That's the rule, and it works for everything. Now here's where things get really interesting. This quantum strangeness isn't just some curiosity for physicists to puzzle over. It explains why you exist. The uncertainty principle. You've probably heard this phrase before. Most people think it means our instruments aren't good enough. That if we just built better equipment, we could measure things more precisely. No, that's completely wrong. The uncertainty principle is not about bad instruments. It's about nature itself. It's a fundamental limit built into reality. Here's what it says. You cannot know both the position of a particle and its momentum at the same time. Not because you're clumsy, not because your measuring device is cheap, but because the particle doesn't have both a definite position and a definite momentum at the same time. Let me make this concrete. Suppose you want to know exactly where an electron is. You confine it to a very small region. Now you know its position very well. But here's the cost. The momentum becomes uncertain. The electron starts jiggling faster it has to, the more precisely you pin down where it is. The more wildly its momentum fluctuates. And it works the other way, too. If you know the momentum very precisely, the position becomes fuzzy. It could be anywhere. Why does this happen? Think about a wave. A perfect wave that goes on forever has a very definite wavelength. You can measure it precisely. But where is the wave? It's everywhere. No specific location. Now think about a short burst, just one little bump. Where is it? Easy. It's right there. But what's its wavelength? Hard to say. It's not really repeating. See the trade-off? A wave that's spread out has a definite wavelength, but no definite position. A wave that's concentrated has a definite position, but no definite wavelength. And in quantum mechanics, wavelength is connected to momentum. Short wavelength means high momentum. Long wavelength means low momentum. So this trade-off becomes a trade-off between position and momentum. It's just how waves work. But here's where it gets really interesting. This explains why atoms exist. Think about it. An atom is a nucleus, positive charge, with electrons around it. Opposite charges attract. So why doesn't the electron just fall into the nucleus? Why doesn't it spiral down and crash? Classical physics has no answer. The electron should radiate energy, lose speed, spiral inward, and collapse onto the nucleus in a tiny fraction of a second. Every atom should collapse. Matter shouldn't exist. But matter does exist. You exist. Why? The uncertainty principle. If the electron fell into the nucleus, we would know exactly where it is. Right there at the center. Position, very precise. But then its momentum becomes very uncertain. The electron would be jiggling incredibly fast, flying off in random directions. It would have enormous energy. So the electron can't stay at the nucleus. It gets pushed out by its own uncertainty. And it can't stay too far away either. The electrical attraction keeps pulling it back. There's a balance, a compromise. The electron settles into a region that's not too small and not too big. And that region is about 1/10 of a billionth of a meter. That's the size of an atom. The size of atoms, the fundamental scale of chemistry, biology, everything around you comes from the uncertainty principle. Without quantum mechanics, there are no atoms. Without atoms, there are no molecules. Without molecules, there's no chemistry. Without chemistry, there's no life. You exist because the uncertainty principle won't let electrons collapse into nuclei. And there's more. This is why you don't fall through the floor. When you stand on the ground, the atoms in your shoes get close to the atoms in the floor. If you try to push them closer, squeeze them into a smaller space, the electrons resist. Their positions would become more certain, which means their momentum would become more uncertain. They'd jiggle faster. They'd push back. That's what solid means. That's what hard means. The resistance of matter to being compressed is a quantum mechanical effect. In classical physics, the best arrangement of positive and negative charges would be all of them sitting on top of each other. Everything collapsed to a point. But quantum mechanics says no. You can't confine particles to a small space without paying the price in momentum. So the next time you sit in a chair and it holds you up, that's quantum mechanics. That's the uncertainty principle keeping you from falling through to the center of the earth. Now here's something else that classical physics got completely wrong. Energy. In the everyday world, energy seems continuous. You can have any amount you want. Push a car a little, it goes a little. Push harder, it goes more. Smooth, gradual. Any value is possible. But in the atomic world, energy comes in steps, specific amounts, like a staircase, not a ramp. Think of a guitar string. It's fixed at both ends. When you pluck it, it vibrates, but it can't vibrate any way it wants. It has a fundamental frequency, the lowest note. Then it has harmonics, higher notes at specific frequencies. You don't get a continuous range, you get specific notes. Same with electrons and atoms. The electron wave has to fit around the nucleus in a certain way. Only certain patterns work, and each pattern has a specific energy. We call these energy levels. When an atom is in a high energy level, it can drop to a lower one, but it has to lose that energy somehow. Where does it go? It comes out as light, a photon, and the photon carries exactly the energy difference between the two levels, not approximately, exactly. Since the energy levels are specific, the energy of the photon is specific, and the energy of a photon determines its color. So each type of atom produces specific colors of light. Hydrogen produces certain colors, helium produces different colors, sodium produces that yellow-orange glow you see in some street lamps. If you look at the light from a distant star through a prism, you see dark lines, specific colors missing. Those are the fingerprints of atoms. Each element absorbs and emits specific frequencies. By reading those lines, we can tell what stars are made of billions of miles away, all because energy in atoms comes in steps. Now let me tell you about something even stranger. Electrons refuse to be in the same state. What does that mean? If you have an atom with many electrons, they don't all crowd into the lowest energy level. That would be the most economical arrangement, right? Everyone on the ground floor. But no, only 2 electrons can occupy each level, and those 2 have to be spinning in opposite directions. After that, the level is full. The next electron has to go to a higher floor. This is called the Pauli exclusion principle, and nobody knows why it's true. It just is. But without it, chemistry wouldn't exist. If all electrons could pile into the lowest level, every atom would behave the same way. Carbon would be like oxygen, would be like iron, no variety. But because electrons have to spread out into different levels, different atoms have different arrangements. Different arrangements mean different chemical behaviors. Carbon acts like carbon, oxygen acts like oxygen. The periodic table, all of chemistry exists because electrons refuse to share the same state. The rules seem arbitrary. Why 2 electrons per level? Why not 3? Why not 10? I don't know. Nobody knows. These are the rules nature plays by. We discovered them by doing experiments. The rules work. They give predictions that match reality. But the deep reason? Still a mystery. Nature has rules. Our job is to discover them, whether they make sense to us or not. So where does all this leave us? We started with a simple question. What is reality? And we ended up having to throw away almost everything we thought we knew. Particles don't have definite positions until you look. They don't take definite paths. They exist as clouds of probability, described by arrows that we add together. The act of observation changes the outcome, and there are fundamental limits to what can be known, not because we're ignorant, but because nature itself is fuzzy at the bottom. This bothers people. It bothered a lot of very smart physicists. Some spent their whole lives trying to find a way around it, trying to prove that underneath all this uncertainty, there must be some hidden machinery, some deeper layer where things make sense again. So far, every attempt has failed. Every experiment confirms the quantum picture. The fuzziness is real. The probabilities are fundamental. There's no hidden clockwork underneath. Now you might ask, if particles don't have definite properties until we measure them, what's really going on? Honest answer? We don't know. The theory doesn't tell us. Quantum mechanics is a set of rules for calculating probabilities. It tells you what you'll observe when you do an experiment. It doesn't tell you what's happening when you're not looking. Some people say the particle is in many states at once until you observe it. Some say there are many parallel worlds where every possibility happens. Some say the question itself is meaningless. We should only talk about what we can measure. These are interpretations, philosophies. They all give the same predictions. There's no experiment that distinguishes between them. But let me tell you what we do know for sure. The theory works. Quantum electrodynamics, the theory of how light and electrons interact, has been tested to extraordinary precision. We can calculate certain quantities to 10 decimal places, and the experiments match 10 decimal places. That's like measuring the distance from one city to another and getting it right to the width of a hair. No other theory in the history of science has been tested this precisely, and quantum mechanics passes every test. So whatever is going on underneath, whatever reality really is, the rules we've discovered are correct. They work, they predict, they explain. And look what they explain. Why atoms exist, why matter is solid, why different elements have different properties, why the sun shines, why chemistry works, why you can see, why you can think. Everything around you, everything you've ever touched, seen, or experienced is made of particles obeying these strange laws. And you don't notice it day to day. The world seems perfectly normal. Objects have positions. Things take definite paths. Why don't we see the quantum strangeness? Because we're big. We're made of billions and billions of atoms. And when you have that many quantum particles together, the weird effects average out. The interference patterns get so fine, you can't detect them. The uncertainties get so small compared to everyday scales that they disappear. The quantum world is always there, underneath, but it's hidden by sheer numbers. So what have we learned? We learned that nature is not obligated to make sense to us. Our brains evolved to track fruit and avoid predators, to deal with medium-sized objects moving at medium speeds. We didn't evolve to understand atoms, and yet somehow we figured it out anyway. That's the amazing part. Not that nature is strange, but that we, these collections of atoms, these temporary patterns of matter, managed to discover the rules. We built detectors and did experiments and wrote down equations, and the equations work. We don't know why the rules are what they are. We don't know what's really happening when we're not looking. We don't have a satisfying picture that fits human intuition. But we have something better than intuition. We have a theory that predicts what will happen, and when we do the experiments, it's right every time. That's physics. That's quantum mechanics. So when someone asks me, what is reality? I have to say, I don't know. I can tell you how to calculate what you'll observe. I can tell you the rules, but what it means, nobody knows. And maybe that's okay. Maybe the question isn't what is reality, but what can we learn about how nature behaves? And that's a question we can answer with experiments, with mathematics, with careful thought. And when we do that, when we actually look at what nature does, instead of insisting it should do what we expect, we find this beautiful, strange, wonderful, quantum mechanical behavior. We find interference of amplitudes. We find uncertainty. We find particles that are neither particles nor waves, but something else entirely. We find a world that's far more interesting than we could have imagined. And that's worth the price of giving up our comfortable classical pictures. I think nature's imagination is so much greater than man's, she's never going to let us relax.